Hello, and welcome to the continuing videos in our linear algebra series. So the purpose of this video is to talk about some of the elimination techniques that we're looking for when we're trying to solve a system. So in previous video, we would have talked about augmented matrices and the rules you're allowed to use, those elementary row operations. So the idea here is, this will be a pretty quick video, is just to talk about where we're going. What are we trying to make it look like? So we saw the example in a previous video that if we had 1, 2, 3, 4, 5, 6, we wanted to turn this into 1, 0, and it turned into -1 and 0, 1, 2. You might even be able to still see it from right here via some steps. Obviously, in a real question, you would write out what those steps were. So the question is, what do we want to make this look like? What do we want that to look like in general? This one seemed to have a beautiful looking submatrix over there on the left side. Looked beautiful. Wants to make this look like x equals -1 down here, 1y equals 2. It was beautiful. It got us to our answer. Is that always possible? Well, we know that it's not always possible because we know that there are some matrices that just don't have exactly one solution. We know that there are systems where there's more equations than unknowns, or vice versa, where we can't expect this to be what we'll eventually call square. And we'll even give that thing a special name, but that's not always possible. So if that's not possible, what are we looking for? So there's basically things that we want to look for. The first thing is we want this first non-zero number to be a 1 if there's a non-zero number at all. We certainly know we might get 0 equals 0. So it's possible to get rows without any non-zero numbers. But if there's a non-zero number, we want that thing to be a 1. We want that thing to be a 1. The first non-zero number should be a 1. Secondly is, once you get that non-zero number to be a 1, you want to get rid of everything that came underneath it. We want, and by get rid of, I don't mean get rid of, turn it into a 0. So everything under that 1, which we're going to call a leading one, or sometimes called a pivot, so the first non-zero number is going to be a 1, called a leading one. Now, not every one you see is a leading one. The word leading means that it's the starting one. If we had another one right here, that's not a leading one. It's just a normal, plain old boring one. Everything under that leading one, we want it to be a 0. And we want these leading ones to move to the right. I mean, that could be a 1 over here. And that's no good, because even though it's a leading one, we want everything under it to be a 0. We want those ones to march to the right. So those are going to be 3 sets of rules that we want our function to look like. And so we're going to call this a matrix is in row echelon form, which we tend to call REF, row echelon form, if 1 for any not all 0 row, the first non-zero entry is a 1, called a leading one or a pivot. 2, any row of all zeros is just at the bottom. Just to get it out of the way. It actually eventually has more of a reason than that. If there's more than one row of zeros, then it's the bottom 2 rows. If there's 5 rows of zeros, it's at the bottom 5 rows, etc. And lastly, the leading ones move to the right as they go down. Now notice how I didn't say moves 1 to the right. I didn't say that. It could move 2 to the right. It just has to move to the right. Now notice here I didn't say a rule that said everything under a leading one had to be 0, but the fact that the leading ones move to the right obviously imply that. Otherwise, if you have a leading 1 to the right, then everything before it has to be 0. And if we also have 4, and you'll notice in our matrix, when we did our example in a previous video, we also turned this 2 into a 0. So technically, this matrix right here is in row echelon form. First non-zero entry is a 1. Any non-zero row is at the bottom, if any exist at all. In this case, they don't exist. And the leading ones move to the right. That's in row echelon form, but we notice that turning that 2 into a 0 made it look a little bit better. So if we also have every entry above, and I'll put in brackets and below. Technically, the and below is redundant because it would have been from the previous rules, but every entry above a leading one is 0. Then we say the matrix is in reduced row echelon form. Some people also say row reduced echelon form, depending on the source. I've seen it both ways. It doesn't change the fact that we have 2 R's before the E and the F. Technically, I believe most sources will say reduced echelon form, but I've heard it as row reduced echelon form as well. So you might see that in other places. And the idea is both of these situations make it easier to find the solution. Reduced echelon form is the easiest to find the solution, but it takes more steps to get there. Row echelon form, it takes a little bit more work to get the solution, but less steps to get into the form. And so there's, depending on the context and what we're using it for, one might be more preferred than the other. All right, so a couple more things. Gaussian elimination basically means we'll take a series of steps and fairly algorithmic steps to turn into row echelon form. Gauss-Jordan. Now, depending on the source you're learning this from, so pay attention to your teacher when you're actually doing the lectures in terms of how specific they want to be in terms of how you turn it into row echelon form. Technically, if you're programming a computer to do this, you would have specific steps in your algorithm to do these. But so it's not just necessarily the case where turning it into REF. Obviously, if you're programming a computer, doing an algorithm, you got to be more specific than that. But that's the basic idea of where we're going with it. So just in terms of some examples of this, Now, in this case here, I'm going to be using augmented matrices, but Gauss or row echelon form, reduced row echelon form is talking about matrices in general, not necessarily augmented matrices. So if that's all the matrices you've seen so far, that's fine. Eventually, you'll see non-augmented matrices, in which case the definitions of row echelon and reduced row echelon form don't change. They stay exactly the same. So here's an example of a matrix here. This would be, again, let's look at the rules. Every non-zero row, in this case, they're all non-zero rows, have leading ones. They move to the right. So this is in row echelon form. Everything above and below those leading ones are zeros. This is in reduced row echelon form. If this was an augmented matrix, we should be able to immediately see what the solution is. Namely, the solution would be that there is none. But that's not the point of reduced row echelon form. The purpose is that we can see what the solution is right away. Not necessarily that it magically makes a solution a specific type, but that we can see the solution right away. This right here, again, with or without the augmented part, is this in row echelon form, reduced row echelon form, or neither? So again, feel free to pause the video and ask yourself, are all those rules satisfied? All right, so the idea here is, yes, they're actually all satisfied, but 3 of them in a really weird way. So I'm going to start with number 2. Number 2 says all the non-zero rows have to be at the bottom, and that's exactly what we have here. So if we have 2 all-zero rows, they have to be the 2 bottom rows. Well, we only have 2 rows, and there are the 2 at the bottom. So that's satisfied. Any non-zero, not all-zero row has to have a leading 1 for the first one. Well, that might seem a little bit weird. This is a little bit maybe of a logic puzzle, or quite often a confusion. But every single row that isn't all zero, the fact that we don't have any of them means that equation or that rule is satisfied. Which might sound a little weird because there's no row that actually satisfies it, but there's also no row that disproves it either. So when we say every single, that is possibly going to be saying that there is none. And if there is nothing that violates that, then we're okay. So that's the first one that's satisfied. In fact, the third and the fourth are satisfied for the same reason. Every single leading one moves to the right. Well, if there isn't any, then that rule is not violated. So when we say these things have to be true, these things are true if there is no row that violates that, then we're still good. So as weird as this might seem at first, this is in reduced row echelon form. Now, what does that mean for a solution if this was an augmented matrix? So again, the fact that it's reduced row echelon form had nothing to do with the augmented stuff. But the idea here is, if we called this x and y, that would say 0x plus 0y is equal to 0. 0x plus 0y is equal to 0. And what x's and y's satisfy that? And the answer, hopefully, would come to you fairly quickly, that any x and y satisfies that. X can be anything, y can be anything. We would say x equals s, y equals t, and s and t can be any real number. So let's think about why we got parameters here. So we got parameters because Well, it's hard to say. Let's pretend this last row wasn't here and we didn't get no solution. If we just had the one above, this would say x equals something. So the fact that we get a leading one here tells us that x has to equal something specific. For this last one, because there was no leading one in the x, also no leading one for the y, there was nothing that said x or y had to equal something, which means they can equal anything. So we're going to call these things, the x and y, free variables. They are free to be anything. And the reason that happened was that there was no leading one in their, well, the column for x. There was no leading one in the column for x, and so it could be free. There was no leading one in the column for y, so it could be free as well. They were free to be anything. Let's try this one, 0, 1, 3, 5, 9, 0, 1, 4, 7, 2, 0, 0, 0, 1, 7. Row echelon form, reduced row echelon form, or neither. So the idea behind this one, again, let's take it one at a time. Every non-zero row, does it have a leading one? Hopefully not too hard to see. Boom, boom, boom. Every row's first non-zero entry, in this case that's every row, had a leading one. There weren't any all zero rows, so they're all at the bottom, they just don't exist. The leading ones move to the right. So this is in row echelon form. Is it in reduced row echelon form? Well, the answer to that is, well, look at this one. Everything above and below it is a 0. Look at the second leading one. Everything above it and below is a 0. Look at this leading one. Everything below is, but not above. So this is row echelon form, but not reduced row echelon form. Which means if we want to get the solution from this, it's not so much immediate. So if this was an augmented matrix, the solution isn't immediate. There's a little bit more work to do, and we'll call that thing back substitution. So, however, are there any free variables in this system? In this case, there is. Remember, the free variables happened when there was no leading one in the column. And when I say the column, the variable columns, not the constant column at the end. This one, let's say x1, x2, x3, and x4, because subscripts are fun. There is no variable or leading one for x3, so we get a free variable for x3. So we get from the last row, x4 equals 7. We also get x3 as a free variable. From the second last equation, we get x2 plus 4x3 plus 7x4 is equal to 2. And now we're going to substitute these two things in. So that's going to say x2 plus 4t plus 7 times 7 equals 2. So move it around. That says x2 is equal to negative 4t. And that's 49. Move that to the other side, minus 47. And the first equation would say x1 plus 3x3 plus 5x4 is equal to 9. Again, we'll substitute everything that came before it. x1 plus 3t plus 5 times 7 equals 9. And so x1 is equal to negative 3t plus 35, move that to the other side, and that's minus 26. And so our solution is x1, x2, x3 is t, x4 is 7, where t is any real number. The idea being is that if we're in row echelon form, or reduced row echelon form would be even better, is that we don't need any more row operations to do it. Although we could use that leading one in column number 4 to get rid of the stuff above. So it's certainly optional, but we don't need any further elementary row operations in order to make it work once we're in at least one of the echelon forms. So those are reduced row echelon forms and how they relate back to our solutions.